Hi everyone, this is Mrs. GA, and today we're going to talk about parent functions and transformations. But first, I have a quick warm-up for you, so please pause the video and give it a try. All right, go ahead and check your work here. For part A, I rewrote this linear equation in slope-intercept form. That's just one way you can graph it. So I saw that y-intercept was -2 and my slope was -1/2. So I went down 1, right 2. For part B, I have this absolute value function. I see that my vertex is at +2, +4. And since my a value is -2/3, that is going to be the slope going to the right, which means the slope to the left of my vertex is +2/3. And you can see my domain and range below. So today we are going to start talking about a concept that we will use in every single unit that we cover this year. We're going to use it over and over and over, which is transformations of functions. So transformations are changes to the size, shape, position, or orientation of a graph. So these rules that we learned today, once you know the rules, you can apply them to any type of function. So at first it might be a little tricky to get these rules down, but once you know them, you can graph any type of function. So there are three main types of transformations. There are translations, stretches or shrinks, and reflections. So a translation is a transformation that shifts your graph left, right, or up and down. So you'll see when you do this, it is a rigid movement. The orientation of your graph is the same. The shape of your graph is the same. It's simply all of the coordinates are shifted horizontally and or vertically. Now, a stretch or shrink is a transformation that multiplies your x or y values, causing it to actually change the shape. So you can see here some different examples. Here would be our parent function. And then this is an example of what a horizontal shrink or compression might look like. So it looks like I put my hands on the outside of our graph and I just push them towards each other, so horizontally. Or maybe you have a horizontal stretch. I put my hands on the outside and I pull them apart. You can also have vertical stretches and shrinks, so that would occur when it would look like you put your hands on top and bottom of your graph and you pull them apart or push them together. And then the last type of transformation is a reflection, and that is when is a transformation that flips your graph over a line. For us, we're going to be reflecting over the x and y axis, so those are the reflections we will work with. So here's your original function. If you flip it over the or the x-axis, it would look something like this. Or maybe you have a function that looks like this, and you reflect it over the y-axis. And there it is. So those are the different types of reflections we will be working with. So again, three main types of transformations: translations, stretches or shrinks, and reflections. All right, so here we're going to look at how these different transformations affect our function, so how they would look in the equation. So you'll notice that these first two are the translations, which remember are the shifts up, down, left, or right. So here we have vertical translations and horizontal translations. So one thing to notice for both of them is that the operation we're using is addition or subtraction. So any type of translation, the way we will apply that to our equation is using addition or subtraction, depending on which way you want to go. Now, if you have a vertical translation, meaning you want to shift your graph up or down, we're going to either add or subtract to the entire function. So we would put parentheses around the entire function and then add or subtract from it. So notice that here we're using the variable k. That's the variable we will always use for these types of translations. So if we add k, it goes up k units, and if we subtract k, it goes down k units. Now for horizontal translations, we're still using addition or subtraction, but you can see here that we're adding or subtracting specifically to x. So you'll notice here that it's grouped in parentheses next to x. That's how we can differentiate between vertical changes and horizontal changes. Now here, with the horizontal changes, you have to be careful. They're actually going to move in the opposite direction that you would think. So here, if you are actually subtracting h, it's actually going to move your graph to the right. And if you add h, it's actually going to move your graph to the left. So with the with the horizontal transformations, you'll see that they are going to act in the opposite way that you think. And here we will always use the variable h for horizontal translations. So again, if it's specifically grouped with x in the parentheses, that's how we know it's horizontal. And if it's done to the entire function, that's how we know it's vertical. Now let's look at the next type of transformation, which were those stretches or shrinks. Now these can be a little bit trickier. So here you'll see that the operation here, this is for a and b. Here we're going to be multiplying. So instead of adding or subtracting, the operation we're using is multiplication. So here you can see that I'm multiplying the entire function by a. Since I'm doing it to the entire function and not specifically to x, this is a vertical stretch or shrink. Now, before you decide if it's a stretch or shrink, you have to look at the value of a. If a is greater than 1, it's going to be a vertical stretch, and we say by a factor of a. Now, if a is less than 1, but still bigger than 0, a is always positive, okay? So if a is less than 1, but still bigger than 0, we actually call that a vertical shrink by a factor of a. So whatever a is going to be your stretch or shrink factor. So again, if a is greater than 1, it's a stretch. If a is between 0 and 1, it's a shrink. And because it's done to your entire function, it is a vertical transformation. Now for the horizontal stretches or shrinks, this is the trickiest one. You'll see that the operation is still multiplication, but this time it's done specifically to x. So again, here you can see that this changes inside the parentheses instead of outside. So that's how we know it's horizontal. Now here, just like there's a special trick for the translations, there is also a special rule for the stretches or shrinks. The factor, the stretch or shrink factor, is actually going to be the reciprocal of b. Reciprocal of b means 1 over b. So that means if b is between 0 and 1, it's actually going to be a stretch because the reciprocal of that would be greater than 1. So you actually look at the stretch factor. If the factor is greater than 1, we call it a stretch. And if the factor is less than 1, we would call it a shrink. So here, when your b value is bigger than 1, the reciprocal is going to end up being less than 1, so we would call it a shrink. So I think this one definitely makes a lot more sense when we do it with real numbers, but just remember there is a special rule for the horizontal stretches or shrinks. But again, any stretch or shrink is going to be done with multiplication. The last type of transformation that we work with are reflections. So there are two types of reflections we will be doing, reflections over the x-axis and reflections over the y-axis. So reflections over the x-axis are actually vertical reflections. It's going from above to below or vice versa. So since it's a vertical type of reflection, the negative is going to be out front. So if you're multiplying your entire function by -1, it will always reflect your graph over the x-axis. So I always say multiplying the y's reflects over the x, and multiplying the x reflects over the y. So if you see that specifically x is being multiplied by -1, it will reflect over the y-axis. So again, for any reflection, it's multiplying by -1. You just have to look at where it's done, whether it's to the entire function or just to x. And that's kind of a common thread. We're always looking at is the transformation being done to the entire function or just to x? To the entire function or just to x? All right, let's give some of these a try. Here we're just going to be describing the transformation using our formal math vocabulary. So here's kind of the checklist I go through. First, I see that this transformation is grouped specifically with x. When I see that, I can write the word horizontal. I know it's affecting my x values, which makes it horizontal. Now, since I see addition or subtraction, I know that that's going to be a translation. And now I just have to decide which way it goes. Since it's horizontal, it's either going to go left or right. But I remember, oh yeah, for the horizontal ones, it's that opposite direction. So even though it says +2, it's actually going to shift our graph left 2 units. So be careful with that. Now let's look at this next one. I see it that we're multiplying something by -1. Anytime we're multiplying by a -1, we know it's a reflection, but now we just have to figure out if it's over the x or y axis. So remember, if you multiply the entire function, it's always going to reflect over the x-axis. Okay, here I look at the type of operation, I see it's multiplication. So I know that it's a stretch or shrink. Since it's being done to the entire function, so again, it's not specifically grouped with x, I'm multiplying my entire function. I know it's going to be vertical. So I know this is a vertical change. Now I have to decide if it's a stretch or shrink. So if it's a vertical stretch or shrink, whatever this number is our factor. And since this factor, 1/2, is less than 1, that makes it a shrink. And then we say by a factor of 1/2. So we're always looking at what the stretch or shrink factor is. And this factor is less than 1, making it a shrink. All right, let's look at this next one. Here again, I see addition and I see that it's done to the entire function. It is not specifically grouped with x. So I know that it's vertical, and because of the addition, I know it's going to be a translation. And for all of the vertical changes, they're very straightforward. If it's +3, it's going to go up 3 units. So it moves in the direction that you would expect. Now here's probably the trickiest one. Here I see that this is being done specifically to x, so I know it's horizontal. I also see that the operation is multiplication, so I know it's going to be a stretch or shrink. But before I decide that, I need to figure out what the factor is. And remember, for the horizontal stretches or shrinks, the factors are always reciprocals. So I'm actually going to write by a factor of first. So if this b value is 1/3, the stretch or shrink factor is the reciprocal of 1/3, which is 3. Now since 3 is bigger than 1, this actually ends up being a horizontal stretch. So I'm going to always look at what the factor is before I decide if it's a stretch or shrink. And again, this number and this number are always going to be reciprocals. That's only for the horizontal stretches or shrinks. All right, last one. Here I see that it's I'm multiplying by -1, so I know that it's a reflection. And since I'm multiplying specifically to x, I know that that always goes over the y-axis. Remember, if you multiply x, it reflects over the y. And there you have it. So now I'd like you to pause the video and give these 4 a try on your own. All right, go ahead and take a look here. Here we have vertical translation because it's being done to our entire function, and I'm adding or subtracting, and this one will go down 7 units. Here I have another vertical change because it's being done to my entire function. It's multiplication, so it's a stretch or shrink, and because the factor is greater than 1, it's a stretch. Here, again, I see that this transformation is being done specifically to x, so it's horizontal. Addition or subtraction tells me translation, and this one's going to move in the opposite direction. This one's actually going to go right 4 units. And last, here, I know this is horizontal because it's specifically done to x. I know that there's that special rule, so the stretch or shrink factor is going to be 1/2, the reciprocal of 2. And since this factor is less than 1, we will call this a horizontal shrink. So just remember, the horizontal changes are the ones that have that kind of special rule that you need to watch out for. All right, so now we're going to try to describe some transformations in an actual equation, and we're going to try to use these transformations to help us graph. So first, I'm going to start by graphing the parent function. I see that this is an absolute value function. So I'm going to start by graphing p of x equals the absolute value of x. So I know that's a graph that has a vertex at the origin, and it has a slope of 1 to the right of the vertex. I usually like to do my parent functions with a dashed line, and then I know it has the opposite slope to the left of my vertex, so like this. Now, before I graph f of x, I want us to describe the transformations. When we're describing transformations and when we apply them, we typically describe anything involving multiplication or division first. So it's just like order of operations. Multiplication or division is what you would do first. So I'm going to address this multiply by 2 first. I can see that I'm multiplying on the outside, so it's not specifically to x. So I know that it must be vertical. And since it is multiplication, it's a stretch or shrink. Now, since this a value is bigger than 1, I know this is going to be a vertical stretch by a factor of 2. So let's talk about how this affects our graph. We're going to actually do each one, we're going to do this in 2 steps. I'm going to look at the points from my parent function, and I'm actually going to double just the y values because it's vertical. So if I double 0, I get 0. So my blue graph is going to be my intermediate graph. Here my y value is 1, so I'm going to double that y value and it becomes 2. Notice that my x value stays the same. Here my y value is 2. I'm going to double that y value and it becomes 4. Here my y value is 3. I'm going to double that and it becomes 6. Here my y value is 4. I'm going to double that and it becomes 8. Same for this y value. I'm going to double it and it becomes 10. So here's kind of my intermediate graph. This is if I just applied the vertical stretch by a factor of 2. All right, now let's look at this translation. So again, I'm adding something outside of my my function. It's not specifically grouped with x, so I know this is going to be a vertical translation. And since I'm adding 5, this is going to push my graph up 5 units. So if I look at my blue graph, which has already been vertically stretched, I'm going to take each coordinate and I'm just going to shift it up 5 units. That's all I'm going to do for every single coordinate. So I'm going to take the one that was at the origin and move it up 5. I'm going to take this and I'm just going to shift it up 5 units. And I'm going to do that with each of my points for as much as I can fit on my axis. So it looks like this. And this is going to be the final result. This is f of x. So if you look at it, we should expect that our vertex is at 0, 5, because h is 0 and k is 5. And then we should expect that the slope of our line to the right is positive 2, and the slope to the left of the vertex is negative 2. So again, we should know how to graph this without using transformations, but I just want you to start seeing how transformations affect your graph and how you can use them to help you graph if you start with your parent function. All right, let's try another one of these together. Here I can see that we just have a nice linear function, so our parent function is just x. So again, that is a function whose y-intercept is the origin and who has a slope of positive 1. So this is p of x. All right, so when we're describing transformations of linear functions, it's a little bit different because here we could actually treat these as horizontal or vertical transformations. I know that it looks like that they are specifically being multiplied to x, but we could also think of it kind of like this. So we could say that it's actually multiplying the entire function. So I will always treat these as vertical transformations rather than horizontal ones. Just makes it a little bit easier. So I see 2 transformations involving multiplication, so it doesn't matter which one you do first or second. So I'm going to start with that negative. I know that a negative makes a reflection, and since, again, I'm treating this as a vertical transformation, I'm multiplying the entire function. I'm going to say it's a reflection over the x-axis, but you're going to see as I do this, it would actually be the same if I said a reflection over the y-axis. So to reflect over the x-axis, I take any point, and I go the same distance away from the x-axis, but on the other side. So this point is 1 unit above the x-axis, so I'm going to place it 1 unit below the x-axis, and of course 0 will stay at 0. This coordinate is 2 units above, so I'm going to place it 2 units below, and I'm going to continue that pattern on both sides. So I just put each coordinate the same distance from the x-axis, but just on the other side of the x-axis. So again, we could have also called this a reflection over the y-axis. You would get exactly the same thing, and that's why with linear functions it's a little different. We could treat this as vertical or horizontal. Now again, this I'm going to treat as a vertical stretch or shrink because I am multiplying. So here I can see that a value is 1/3, and since that is less than 1, we would say that this is a vertical shrink by a factor of 1/3. So that means that I would take all of my y values from my transformed graph and I would multiply them by 1/3. Just to make this a little bit easier, I'm going to pick nice numbers. Like here I see that my y value is -3, so -3 times 1/3 is -1. I'm going to pick this one where it's -6. -6 times 1/3 is -2. So I'm going to pick numbers that are divisible by 3 just to make my life a little bit easier, but you don't have to. You can always estimate. Okay, and here is my final graph. And this is f of x. Now, of course, we should be able to graph this function without using transformations. We know the y-intercept is 0 and the slope is -1/3. But again, I just wanted to show you how we can use transformations to graph, starting with the parent function and then just applying one transformation at a time. All right, let's try one more together. So remember, we're going to start, if we're using transformations to graph, with our parent function, which again in this case is absolute value of x. So let's do that really quick. Okay, this is p of x. Now again, we always start with transformations involving multiplication or division, or multiplying by a fraction. So here I can see we're going to start with this reflection. I see that the negative is not specifically grouped with x, so it's going to be a reflection over the x-axis. So I'm going to take, again, all of my coordinates and I'm going to move them the same distance from the x-axis, just on the other side of the x-axis. So it ends up looking like this. And again, this is just that intermediate step. I'm not completely done, so I'm going to keep it as a dotted line. And now I'm going to look at the addition and subtraction. So here I can see that I'm specifically adding 4 to x, making it a horizontal translation. Horizontal translation. And remember, that will go in the opposite direction that we think. So this is going to go left 4 units. And then I see here I'm adding or subtracting to the entire function, so outside of the absolute value. So that's going to be a vertical translation down 2 units. So remember, with the vertical translations, it's going to go in exactly the direction you think. If you subtract, you're going to move down. So I'm going to see if we could do both of these in one step. I'm going to take every coordinate and I'm going to move it left 4 units and down 2 units. So the coordinate that was the origin is moved to here. Let's do this coordinate. Go left 4, down 2. And you can kind of continue that pattern. Left 4, down 2. So you're going to do that to all of your coordinates, and you will end up with f of x, a nice graph of f of x. And again, I know that we already know how to graph this. We should be able to look at this function and say, okay, the vertex is at -4, -2, which it ends up being there. And we can see that since my a value is -1, the slope of the line to the right is -1. So we should be able to graph this without transformations, but now you can see how those transformations have affected our parent function. All right, here I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check here. So what I'd really like you to focus on is how you describe the transformations. So you should have that reflection over the x-axis, vertical stretch by a factor of 3/2. Remember, the negative and the a value are different transformations. And then a horizontal translation, right 1 unit, opposite direction, and then a vertical translation, up 3 units. So you can see first I reflected, and then I did my vertical stretch, which is that green graph, and then I shifted all of my coordinates right 1 and up 3. So again, I'm not saying you have to graph these types of functions in this way. We should know the vertex is 1, 3, and we should know the slope to the right is -3/2. And of course, that's much faster. It's a lot more efficient. But just for the sake of today, we're practicing describing and using transformations. Okay, I have one last example for you to try. So again, pause the video and give it a shot. All right, again, go ahead and check your transformations here. We should have a vertical shrink by a factor of 1/4, and then a vertical translation down 3 units. So here, it is not being subtracted just from the x, or else you would see parentheses around just the x minus 3. Now, again, this would not be the most efficient way for us to graph. I would rather you use the y-intercept at -3 and then follow a slope of 1/4. But just for the sake of understanding how transformations affect our graphs, I think this is a really valuable exercise. All right, that is all for today's lesson. Thank you so much for watching.